And we're going to look some more at these radicals. We're going to simplify them today. We've talked about simplifying square roots. Today we're going to talk a little bit more about cube roots and fourth roots and that sort of thing. So we start off with, this is one you've seen before, square root of 24. You want the largest perfect square that divides evenly into 24, and that's 4. Square root of 4 times the square root of 6 is square root of 24. And when I take the square root of 4, that gives me 2. And the square root of 6, I cannot simplify any further. So when you have a problem like this, the cube root of 16, all right, the cube root of 16, you want to find the largest perfect cube that divides evenly into 16. The largest perfect cube that divides evenly into 16 is 8. And it's 8 times 2 is the square root of 16. The cube root of 8 is 2, and it leaves me with 2 times the cube root of 2, which cannot be simplified any further. Back to square roots. If I have 4 times the square root of 50 times x to the 5th, the largest perfect square that divides evenly into 50 is 25, and that's 25 times 2. And the largest perfect square that divides evenly into x to the 5th is x to the 4th. Remember, that would be an even number. So x to the 4th and x to the 4th times x is this x to the 5th. Well, square root of 25 is 5. The square root of x to the 4th is x squared. And that leaves me with the square root of 2x. And then 4 times 5 times x squared is 20x squared times the square root of 2x. Now let's do it with fourth root problems. Here we have 64, and I apologize, I didn't have my stylus today, so this is done by hand. This is the fourth root of 64, a to the 4th, b to the 5th. And so I find the largest perfect fourth power number, which is 16. 2 to the 4th is 16. A to the 4th is a perfect fourth root that divides evenly into a to the 4th, and b to the 4th is the largest fourth root that divides evenly into b to the 5th. So the fourth root of 16 is 2. The fourth root of a to the 4th is a. The fourth root of b to the 4th is b. And that leaves me with the fourth root of 4b that still cannot be simplified any further. We could also add these together, and the easiest thing to do is to get them all with the same radical underneath the radical. So I simplify the square root of 12 to be 2 square root 3. That's already got a radical 3, and square root of 108 is 6 times the square root of 3. So then now the square root of 3's act like a variable, and we have 2 minus 2 plus 6 is 6 square roots of 3. Just as before, we cannot leave a square root in the denominator, so I cannot leave a cube root in the denominator. But in this case, I'm not just going to multiply by the cube root of 9 over the cube root of 9. I have to multiply by what's going to make this a perfect cube. 27 is a perfect cube. 3 times 9 is 27. Square root of 20, cube root of 27 is 3. So I have gotten rid of the radicals in the denominator, and then the cube root of 2 times the cube root of 3 is the cube root of 6, and that can't be simplified any further. Here, this is sort of like a FOIL problem. Everything gets multiplied by everything. So 4 times 3 is the 12. 12 times 20 is 240. And the square root of 240 is 4 times the square root of 15. 12 times 4 is 48, so you're left with 48 times the square root of 15. So we're going to be adding, subtracting, multiplying, and dividing with a whole bunch of radicals that aren't necessarily square roots. They may be cube roots or fourth roots or even higher.